You must be Pam?
I am.
Hi,
I
Mike.
must be Mike.
Pleasure to meet you.
I have a attendance thing I need to pass around.
Okay.
Okay? Is that all right? I'll go get it because I didn't know if you were here. I thought you might be, but you can bring it with me.
Oh, great. I'm here. Bring more people in.
You're supposed to have about 8 or 9.
Okay, great. Thank you. Well, if it's just the three of us, it could be really short.
How do you pronounce your last name?
Well, it's kind of tough because in Italy they say Celentano, but in Indiana it's Celentano. As long as you don't call me late for dinner, I'm fine with Mike. Mike is fine.
Yeah, I got you.
Can you make the slides available to the students that attend?
Yeah, if you mail them to me.
Okay, I just did actually, so should be in your inbox.
I can do it when I know who's attended. I can.
That sounds good.
I'm hoping that you have more than 2 that show up because they're going to get dinged for not being here.
Yeah, I hope so too. Do you want to wait 5 minutes or whatever?
I will.
Okay, sounds good. Hey, welcome. We're going to get started in about 5 minutes or so.
I'm trying to go on the next implementation trip in May.
Cool. Do you like that organization? I was thinking about checking them out.
It's nice.
Is it mostly
Pretty good structure.
power and water and stuff like that, or
It's mostly water.
mostly water?
Yeah. There are various other projects that you can find for some power, some like structures, like some bridges and stuff, but it's mostly water.
Cool. That makes sense. I mean, you think about the world's needs, water is kind of top of the list. Not much engineers can do about political strife. So we'll get started in a couple of minutes. We're going to wait to see 2, 4, 6, maybe 2 more people might come. We have a sign-in sheet going around. So all of you already have a project, or is anyone looking for a project? All on projects now? Cool. Engineers Without Borders, any other groups? Same? How about you folks? Oh, neat. Museum? Nice. How about you folks? Oh, neat. Okay. I haven't heard of that. What do they do? Cool. How about you? Oh, nice. Good. Like medical instruments almost.
More like so they can participate in everyday activities.
Ah, all right. Accessories, that kind of stuff. Do you ever get into like fake limbs or anything like that?
Probably the closest is probably like allowing them to like ride a bike, like if they don't have an arm or something, then we provide like a cup for them so they can steer it.
Oh, cool. That's nice. That's good. Yeah, the idea of EPICS, right, is to help society with engineering, right? Am I getting that wrong? It's a good thing. All right, I probably won't want to wait any longer. Sorry for holding you all up. We'll officially get started here. So, hi everybody, good evening. My name's Mike Celentano. In Italy they say Celentano, but I'm fine either way. I've been working in systems engineering for about 30 years or so, mostly in medical devices. And in fact, the first medical device that I worked on is this big guy over here. And that was really fun. And that's the thing that got me hooked on systems engineering, because they had like mechanical engineers, electrical engineers, and fluidic engineers, and doctors, optical engineers, all working together on that. It's a big, like, giant clinical analyzer. And so I got the bug then, because I like all disciplines. And so that's why I got into systems engineering. So I'm going to give you today a kind of crash course on SE processes and activities. And one of two means that my colleague from INCOSE, Chris, he's going to follow up on architecture in a part 2 thing and really focus on best practices there. And so what was left for me was everything. So I'm happy to do that, but it's going to be kind of hard on you. So I'm going to go really fast and maybe take up the whole hour. So sorry, but I'm going to leave 15 minutes at the end for discussion and for questions and stuff like that. But first we're going to go over system engineering at a glance, which includes systems engineering, system thinking definitions, what's life cycles and what's tailoring, technical management, technical processes, and specialty stuff. And along the way, I'm going to be popping in some suggestions and some methods and even giving you templates in this slideshow. And Pam, I forget her last name, I apologize, said that she'd email you guys this PowerPoint slide so you can use the templates if you want. And after I'm done getting through kind of the at-a-glance stuff, I'm going to come back around and touch again on all the methods that I selected so that we reinforce it and also give you a little bit more information about the templates and that kind of thing. Sound good? All right, and then at the end, I'm going to give you some valuable references. And, well, there's a lot here, so I'll get started. So what's systems engineering? There's a lot of definitions for it, but my favorite ones come from INCOSE and myself. INCOSE is the International Council on Systems Engineering. And like the name suggests, it's everyone in the world getting together that's system engineers and helping to define standards for it. So essentially, systems engineering really focuses on the interdisciplinary approach, which I mentioned before. That's the reason why I got into it. It helps identify customer needs and making sure that the customer is satisfied with the product or system that you're working on. But the other thing is that it really focuses on understanding the technical needs, the business needs, and the interfaces in your system so that you can optimize it in a way that doesn't cause some more problems down the road. My favorite part of it is the interfaces and the cross-discipline stuff. And if I had to give an elevator speech on what systems engineering is, I would say it's about the interfaces between people, machines, machines, and machines, and people to people as well. Systems thinking, you've probably heard of this. It's like systems engineering, except for more theoretical. And with systems thinking, there are, again, multiple definitions. These are the most common ones. I like mine the best, which is don't be that person that makes a solution looking for a problem. So the idea there is if you have a problem, spend time defining what the problem is, what the goals need to be to fix that problem, and then design your system rather than designing something and then trying to find someone who wants it. But I have to give people here credit for thinking really strong. Some of these people spent their whole life on systems thinking, and these are better definitions than mine, probably more well thought out. But really, systems thinking is this kind of framework of analytical principles and concepts that are based in science, that are applied to problems in order to make sure that you're addressing the problems correctly, and then your solutions will be better. Does that make sense? Okay. So, as I promised, there's some tidbits of valuable references. This one's from Systems Praxis, which you can go online and look this up. And there was a group of people from multiple organizations that got together and tried to define the relationship between systems thinking, systems science, and practicing systems approaches or systems engineering. The bottom bubble is kind of where system engineers play. We're mostly practitioners. We're not theorists or philosophers. We like getting projects done. But there are people on the top of the cloud here that are real thinkers and philosophers and scientists that have done research on what does it mean to think about things from a system perspective. And they have a series of principles and concepts that are applied called system thinking that then is related to systems engineering on the bottom. There's a lot here, but I think the bottom line is that systems thinking is based on system science and uses these principles that I talked about. Again, you can spend a lot of time here studying this, but I think there are some system concepts worth thinking about. Like one very popular concept is this Iceberg Model. You may have seen it before. It's referenced many times in literature. But here's what this is saying. It's saying if you want to change the way someone's doing business, or if you want to change the way that an organization is behaving, or if you want to change the way a system's behaving, you have to understand all the reasons why it is. And a lot of these things are based on people. And so when you think about why a person does what they do, you have to think about all the things you don't see on the surface, like their mental models, their underlying structures, the patterns, and the things that they're exposed to. It's the same with systems, too. People are a type of system. So in a lot of cases, when you're trying to do systems thinking, it really helps to think about what's below the surface, what are the reasons why things are happening, and what. Now, if you really want to get into it, there's a list of, at SEBOC, that's System Engineering Body of Knowledge.org. It's another great reference. On their section on systems thinking, they have the definitions of all of these different systems thinking principles. Some of them you've probably heard of before, others not so much. But they all have to do with it, like the thing I showed you before, they all have to do with these different kind of philosophical principles that are the basis for what systems thinking really is. One of my favorites, as I mentioned before, are related to things like interaction. And interaction, again, means what are the exchanges of either information, data, energy, whatever, between two systems or subsystems. But there are a lot of others here, too, that are important. Any questions? SpongeBob's still thinking about it there. So I wanted to talk a little bit about tailoring. This is not like the material tailoring. This is tailoring in the sense of trying to change what you find in a textbook and apply it to an actual project. It means that you need to make something practical. And basically, there's a whole kind of approach to that. And that approach simply is just making sure that you're taking the method, let's say, that you're about ready to start, and really thinking about how does this really apply, and where does it not apply, and how do I use it? So again, applying a little bit of systems thinking to some of these methods might help you in your project. Don't be afraid to tailor them to either the size of your project or to the needs of your project, because that's some of what systems engineering does too, is tailor approaches to fit the situation as good as possible. But it can apply to documentation, processes, scope, analysis, decision making, and of course, it all needs to be consistent with whatever statutory requirements, meaning whatever regulations there might be. So if you're working with Engineers Without Borders, there's probably a set of bylaws or whatever that you have to comply with. You don't want to go outside of that, of course. Okay, so life cycles. Who's heard of life cycles here? That word. 1, 2, 3, 4, maybe. Okay, so what is a life cycle? Well, a life cycle has to do with trying to define the stages and the gates that are necessary in your project to get from the beginning to the end. And there are a lot of standardized life cycles for these kinds of things, and some of them are waterfall type, and others are iterative. And it turns out that anything on a piece of paper really is not representative of real life, but they're approximations to help guide a team in the same direction. So in this case, on the left-hand side, one of my favorites is the FDA system life cycle, which starts with user needs and then goes down to design input, and then to the design process itself, and then to design output, and then the design output is verified by comparing it to design input, and then the design output goes to be made into a medical device, which is then validated against the user needs, and along the whole way they review. Does that make sense? So that describes kind of the process of how you need to do your project if you're going to qualify for design control within the FDA. So they actually are a regulated body, and that's what they suggest you do. But there are other people who have taken different approaches. Like, for instance, this V shape here is something that's actually a V diagram that comes from a guy by the name of Kevin Forsberg back in the 90s. And Kevin defined this kind of V where he said, hey, on the left side of the V should be all the stuff that defines the problem. And on the right side of the V should be all the stuff that defines how you're going to test that you actually solve that problem. And the point in the bottom is mostly your real design. So in other words, you don't want to do design until you define the problem, and you want to trace from your problem definition over to your test that way. And this is broken into phases. And this was tailored by the California Department of Transportation, and it's a really good example of tailoring where they just kind of plopped in their own process in there. Another person that's really famous in this space is Boehm. And Boehm was like the first person to really popularize this idea of iterative development, spiral development in this case. And that's a little more realistic on reality. In other words, instead of saying this is a one-way path going down here like the FDA does, what this says is you're going to do that once and then come back around and do it again, et cetera. And that's a little more realistic, iterations basically. And then in the extreme, you've heard of Agile. Well, this is the extreme Agile for the whole organization called SAFE. If you're ever interested in that, look it up, SAFE. It's really cool. They're not only doing Agile in projects, but they're doing them in programs and in the portfolio level as well. Any questions? All right, you haven't fallen asleep yet. That's good. So in the System Engineering Handbook, there's major sections, 3 major sections. One is called, and we get certified based on the handbook, but one is called technical management. And so this is kind of an overview of technical management. So there's project planning, project assessment and control, decision management, risk management, configuration management, information management, measurement and metrics, quality assurance, technical assessment, and technical readiness levels. Wow. And that's just 1/3 of that whole thing. So I can't cover it all. But what I can do is kind of give you a taste of what's going on here. And that is, in technical management, what they're trying to do is teach systems engineers that we have to be involved in the planning process, and we have to have good decision making, and we need to make sure that when things are changing that we control those changes, and that we have the right metrics in place and the right quality in place, and we make sure that we measure things like technical readiness. And the things that are asterisks are things that I'm going to spend a little bit more time on, because I think they're probably the most important things out of this: project planning, decision management, risk management, and technical assessment if you're working on a project. So project planning. There's something called the System Engineering Management Plan that's very popular with system engineers. And NASA, Department of Defense, Department of Energy, all these big technology organizations use system engineering management plans to supplement their development plans. And there's a long list of stuff that they expect in this outline. So I've got that on the left-hand side. But then I thought, hey, that's really for making a missile. And I don't think anybody here is making a missile. So I thought, hey, let's tailor this for a student project. And on the right-hand side, what I did was I tailored it for student projects. And basically, this is my suggestion here, is that you should always define what your purpose and scope of your project is, You should decide what your life cycle is. Remember that, what that was? That was the stages and the gates that you need to get from the beginning to the end. And then you should know what your rubric is. How are you going to be judged by your stakeholders, maybe your teachers in this case. You should have a plan for how you're going to get your requirements, how you're going to manage risk, and then you should kind of describe what you think your solution is going to be. And can't forget that if you have a team, you want to kind of divide up the tasks into assignments. I call them subsystem assignments. And then have a plan for how you're going to integrate all your work together, verify that you did it right, and then validate that the customer actually wants it. And then, list out your milestones and deliverables, any tools or resources, and you might throw in some extra stuff in the appendices. How's that sound? So how many people actually have a plan for the project they're on now? 1, 1.5, 2, 2.5. Okay, that's not bad. I would suggest spending a little time with your team on that if you don't have one. And if you do already, if there's anything that inspires you, maybe you can add that in. But one of the things that I've learned is that a plan that kind of sits on the desk after you look at it is no good. Actually, a good plan is one that you actually update, revise, and follow. And the other thing is you do need the right size for the size of your project. So if it's only 2 working on a project, the only plan you probably need is like a 1-pager that says you're going to do that and I'm going to do this and we're done. But if you've got maybe 3 or 4 people, then I think you need a little more formality. Sound good? Question?
How do you integrate this into a system where there's constantly changing individuals and like management?
Constantly changing what?
Like individuals and like workers and management.
Oh yeah, that's a good point. So if you have the same goal, right, and let's say you have a goal to install, tell me what your goal is, for instance. Build a park. So if you have the same goal as a park, what you could do is you could define your plan in terms of roles, not actual people's names. You could say, this person is responsible for the mulch, this person is responsible for the playground, this person is responsible for the fencing, whatever it is. And this person, instead of actually writing in just the name there, you can give them roles so that if someone comes and goes, if someone goes out, you're like, hey, I'm looking for a person to do this role, and then you assign that role. Does that make sense? And if you write down the plan, it's really cool because then everyone knows what you're doing, and when the new person comes on, you're like, here, this is what we're doing, and this is where you are. Cross out that name, put in your name, that kind of thing. Does that sound helpful? Cool. Any other questions? All right. So here's something called trait analysis. This is maybe not as commonly known in the lexicon of college students, but trait analysis is really an important aspect of systems engineering. Basically what it means is if you think you have a solution, you ought to have more than one possible solution because that means that you're too narrow. Let's say you have 3 or 5 possible solutions. How do you compare them to each other? Well, that's what this is. This is a trait analysis where you say, I need to understand what my criteria for a goodness is, and I need to then measure each one of these, philosophically measure them, or qualify them, and then compare them to each other. But there are common essential trait analysis steps, which includes getting with the stakeholders and the subject matter experts, SMEs, frame the problem or the decision to be made, define the key values or criteria for the stakeholders, because really your stakeholders are like either your customers or the people who are paying you or the people who are in control of the whole thing. You want to make sure that you understand what's valuable to them and that when you choose which solution is the best, it's the one that has the best value to them. Plus, you want to include them in the process, too, so that they're not surprised. Analyze how each one meets the criteria, compare and discuss the results, and then agree on the ranking, and document the reasoning and decision. So if you've got an important decision to make, like, hey, I've got 3 possible solutions, let's decide which one we're going to do because we can't do all 3, then that's worth doing. But if you're trying to decide on which part I'm going to use and it's not critical and it's like a resistor, should I buy it from DigiKey or should I buy it from Molex or whatever, that's not worth a trait analysis. So what are trait analysis? Basically, these trait analysis things are tables. They're like Excel tables. They're either weighted or relative or comparative. There are some examples of weighted over here on the right-hand side where each of the criteria has a weighting, and that weighting comes from your stakeholders, basically. Which is more important? Well, in this case, the one that has a 4, friction performance, for this stakeholder was the most important. So they gave it the highest weight. And then when you grade each one, this was gel, and I forget what this one is here, liquid and hybrid, you get a chance to actually grade each one and then multiply it through, get the weighted rating, and then add up which one's the winner. That's the way to do it, by a weighting scale. You don't have to weight it. You could do like a, is it better than the existing concept, or is it worse, pluses and minuses, relative? Or you could even do pros and cons. The point is, you're getting the team and the stakeholders together to make a decision together which one of these particular options is better for the group. You can get really crazy with it too. There's a great example in the CBOC, I mentioned CBOC before, where this is really comprehensive. They even have little images of the different options here. These are different kind of planes. They have color coding and scoring and all that kind of stuff, which I think is really cool. In practice, though, after many years of doing that, I've realized that no matter what, even if you have like a nice score, you still have to have a discussion with the people to say, is this really the best one? And then what happens with scoring sometimes is people are like, no, wait a minute, we need to change that weight to a 5, because they're adding it up in their head saying, now my idea is going to get better if I add that 5. And so there's gaming of numbers and stuff. So in practice, what I found actually, it's better to, this is just me, if you want to do the weighting thing, you can. There's lots of information out there on how to do that. I actually like doing this, which is the Celentano trait analysis method. And that forces the team to define the problem statement, define the criteria, what's acceptable and what do you wish for, list each one of your ideas, and then state how does it fit to the criteria, list the pros and the cons, and then talk about the rankings and the reasoning. Notice there's no math in here. The reason why I think no math is better is because this is all about the conversation. It's, yeah, I think this one's the best because it has the lowest price and it also has the lowest risk, right? And, you know, that's, in this case, hard to argue with. But in a lot of cases, people that are doing weighting might come back and say, oh, no, there's a different criteria, and they start adding stuff on. So it's all, to me, it ends up all being about that conversation. You still want the criteria. You still want an agreement on this is all the important stuff, and then the comparison's important. But this is the part that you can't replace a number with. It's the discussion and the agreement on the reasoning. Sound good? You're welcome to use the Celentano trait analysis anytime you want. You don't have to call it that either. OK, let's jump to something else called risk management. And you've probably heard of risk management. But in this case, I'm going to focus on, there are many different ways. So I'm going to focus on failure modes and effect analysis. But there are things like fault tree analysis, system risk analysis, and all sorts of wonderful tools that you could use instead. I like the FMEA because the FMEA is at the right level of abstraction for the things that I do. So the idea of an FMEA is when you're defining your solution, you try to kind of map out what are all the subsystems that I have and the interactions between them. And let's say I'm building a playground, for instance, and I've divided up the work into 4 people. And those 4 people are like fencing, mulch, play set, and I don't know, walkway or something like that. And it seems like it's going to be super easy to get that done. But just with those 4 things, you can think about a number of interactions between those things. You don't want the walkway to go right through the play set. And you don't want the mulch to be on the walkway. And you don't want the fence to be on either one of those. So there are very simple, like little diagrams that you can make that say, these are the interactions that we don't want. And the interactions you don't want are actually the things that go into a failure mode and effects analysis. Once you know what the interactions you do want are, you could just look at them and say, what happens if that doesn't happen? And how can I avoid that from happening? So it doesn't need to be as complicated as this, but you do need to know what your interactions are. Here's an example. And I forgot